This is the packet for discrete random variables, page 1. Basically, this first page is talking about how with any kind of group of probabilities describing all the possible situations that can happen in an experiment. Basically, the probabilities have to add up to 100%, right? They have to add up to a probability of 1. Otherwise, you're not accounting for everything, right? So, and in these cases, we are accounting for everything, so they have to add up to 1. Okay, so that's the principle we use to solve these problems. Okay, so consider these three tables. State which tables could not represent a discrete probability distribution, giving reasons. Okay, so for example, for this first one, it says, okay, the probability that a 1 occurs, a 2 occurs, a 3 occurs, and a 7 occurs are 0.1, 0.2, 0.03, and 0.4. The thing that you need to check is, do these probabilities add up to 1? And if they do add up to 1, then that could be a probability distribution. Okay, so 0.1 plus 0.2 is 0.3, plus 0.03 is 0.33, plus 0.4 is 0.73. So it's a total of 0.73. So no, this is not a probability distribution. It has to add up to 1. Now let's look at this one. 0.1 plus negative 0.2. That's weird. How can you have a probability that's negative? You can't. So this probability distribution is also illegal because it doesn't have all positive numbers. Look at this last one. So now we're going to add up 0.2, 0.2, 0.5, and 0.1. Those add up to exactly 1.0. So yes, and they're all positive too. So yes, this one can be a probability distribution. So this one can be because adds up to 1 and all positive. And the other ones, this one has a negative number, and this one doesn't add up to 1, right? Okay, number 3. So here's a function which is basically divide the input number by 19. And the domain are the numbers 1, 5, 7, and k. We don't know what k is. Defines the discrete probability distribution, find the value of k. Okay, so basically what they're saying is, it's like a table, kind of like this one, except the table is going to have 4 possibilities, 1, 5, 7, and k, and the probability for each one is dependent on the value of x. So for example, the first one, the probability is 1 over 19. And the probability of a 1 occurring is 1 over 19. The probability of a 5 occurring is 5 over 19. Do you see how this works? You just plug in the x value here into the formula, and that gives you the probability for that number occurring. And then 7 occurring, that's 7 over 19. And then k occurring, that would be k over 19. So we don't really know yet what that probability is. And they say that this is a valid probability distribution, which means that all these numbers down here, the probability numbers, must be positive numbers, and they must add up to 1. So if I add up 1 over 19 plus 5 over 19 plus 7 over 19 plus k over 19, I should get 19 over 19, which means that 1 plus 5 plus 7 plus k has to add up to 19. So that means that 1 plus 5 plus 7, which is 13 over 19 plus k over 19 must be 19 over 19, which means that k looks like it should be 19 minus 13, should be 6, right? So if k is 6, that would make this true. 13 over 19 plus 6 over 19 is 19 over 19. Okay, and it must be 6 in order for all these probabilities together to add up to 1, which is 19 over 19. Sorry to bring back bad memories with fractions there. Okay, let's move on to number 5. The probability distribution of a discrete random variable A is defined in this table. There's a lot of letters and stuff, here and here. The main thing is that the top row is the number that occurs in your experiment. And the bottom row is the probability of each of those corresponding numbers, okay? Let's see. First, we're going to find that the probability that a 12 occurs. So what's the probability that a 12 occurs? Oh, we don't know. It's blank here. But we do know that all of these added together have to add up to 1, right? And we know it has to be a positive number. So what if we added up all these numbers? So 0.5 plus 0.05 is 0.55. 0.55 plus 0.04 is 0.59. 0.59 plus 0.1 is 0.69. 0.69 plus 0.2 is 0.89. So on the calculator, if you would just like add up 1, 2, 3, 4, these 5 numbers, you would get 0.89, which means that this last one is equal to 1 minus 0.89, the difference between 1 and 0.89, so it would be 0.11, right? And what about the probability that A is no more than 9? No more than 9. What does that mean, no more than 9? So no more than 9 would mean it could be 5, it could be 8, and it could be 9, because 9 is no more than 9. Could it be 10, 11, or 12? No. So basically when it says no more than 9, that's the probability of 5, 8, or 9. So we could just add those 3 probabilities together, right? So 0.5 plus 0.05 is 0.55, plus 0.04 is 0.59. What's the probability that A is at least 10? So A is at least 10. Would that be 10, 11, 12? Would that include 10? Yeah, at least 10 includes 10. So now what we're going to do, and remember this last one is 0.11. We just found that out in part A. At least 10 would be 0.1 plus 0.2 plus 0.11. So that would be 0.41. And now here's a tricky one. The probability that A is greater than 8 given that A is less than or equal to 11. So for this one, what you want to do is you want to look in the formula sheet. And the formula sheet tells you that the probability of A given B is equal to the probability of both A and B happening divided by the probability that only B happens. So what's the probability that A is greater than 8 and A is less than or equal to 11? That means that the number is between 8 and 11, right? So that would be 8, 9, 10, 11. Let's just check to make sure. So greater than 8, oh, greater than 8, does that include 8 itself? No, it doesn't. And what about less than or equal to 11? Does that include 11? Yes, it does. So basically, the probability that both happening is 9, 10, and 11 occurring, which would be 0.04 plus 0.1 plus 0.2. So that would be 0.34 for the top. And the probability that only B happens would be the probability that A is less than or equal to 11, okay, which we already calculated. That would be all of these together. We already calculated at the beginning that was 0.89. Okay, so you could just write this as a fraction if you want to. You just multiply both 0.34 and 0.89 by 100 and you get 34 over 89. But the easiest way to do it would be just to put 0.34 and 0.89 in the calculator, and then we'll get a decimal. Okay, so 0.34 divided by 0.89 is 0.382. Okay, all right. Last one, number 7. Part of the discrete probability distribution of the discrete random variable t with the domain 1, 2, 3, 4, 5 is shown in the bar chart. Okay, so this is a little bit different representation. Before we always looked at tables. Now we actually have a little bar chart for the table. And the bar chart indicates the probability of each number occurring. So the probability that 1 occurs is 0.2. The probability that 2 occurs is 0.15, etc. So what they want to do is they want us to make bars for 4 and 5 using the information they give us here. They said that the probability that t equals 4 is 4 times the probability that t equals 5. So for example, if we have a little short bar here, then the 4 bar should be 4 times higher than the 5 bar. But we do need to use the constraint that we already know that all the probabilities must be positive, which they appear to be, right? And the probabilities added together must add up to 1. So let's see. basically what we got is we got the first bar, which is 0.2. We got the second bar, which is 0.15. And we got the third bar, which is 0.1. And then we're going to add that to 4 and 5, right? And for 4 and 5, let's say that 5 is height x. 4 would be height 4x because it's 4 times as tall, right? So I'm going to add 4x and x. And that should equal 1. So let's see, 0.2 plus 0.15 plus 0.1, that would be 0.45 plus 5x, I combine 4x and 1x, equals 1. And then I'm going to subtract 0.45 from both sides so that I end up with 0.45x, and 1 minus 0.45 is 0.55. You can do that on the calculator. And then I divide both sides by 5, and then I find out that x is equal to 0.11, which means that the probability for 5 is 0.11, and the probability for 4 would be 4 times that. It would be 0.44. So you can see I drew these way too small, right? So 0.11 would be about that tall, right? And 0.44 would be so tall that it would go past the limits on this bar graph. Okay? Yeah, so it says construct the probability distribution table for t. I guess that what they want is they want this table with the values here. So 1, 2, 3, 4, 5. The value for 1 is 0.2. The value for 2 is 0.15. The value for 3 is 0.1. The value for 4, like we said, is 0.44. And the value for 5 is 0.11. And we could put here that the headings for the table, it would be the first row would be the probability that t happens, right? T. And then this would be the probability that big T equals little t. So that's how you write that. It's not that important that you know how to write these notations here, because probably on the exam they would provide at least the headers for you to fill that in. Okay?